Statisticians often prefer to describe variation with a single number, okay? And we've already talked about the range not being a great measure of variation, and instead they prefer, and these aren't the only measures of variation, by the way, but they prefer the variance and the standard deviation because it takes all the data into consideration. Remember that the range only used the highest and lowest value and was very, very influenced by extreme values, so it was kind of not a very good measure. But this one will take all measures into consideration. I'm going to derive the formula in a very loose way, just so that you get kind of a feel for why this actually works, okay? And it will also give you a little bit more insight on the mean. Remember our accident data that we've been working with all along. And remember also that if you go back and look at measures of central tendency, we did calculate the mean for this data to be equal to 10. And remember also that when all the values are identical, the mean provides perfect information. So the example I gave in class is that if everybody gets a 90 on the exam, so everybody has an identical score, the mean will actually be 90. So the mean is giving us perfect information about what's going on. So hopefully it will make sense to you that we should be looking at how far the values are from the mean. Okay, so if the values are closer to the mean, we'd expect less variation. So we're going to calculate something called a deviation. Okay, basically we're going to see how far each value is from the mean by subtracting. So we're going to take each of these x values and we're going to subtract off the mean. Okay, so we have 6 minus 10, which is going to give us a negative 4. 7 minus 10, which is a negative 3, 9 minus 10, negative 1, and so on. So we're going to get a negative 6. 27 minus 10 is 17. And then we're going to get a negative 1 and a negative 2. So now we know how much each value deviates from the mean. But remember that we are actually looking for a single number, one number that describes the variation. So hopefully, so we want to condense this information into a single measure of variability. And so we might be looking, for example, at maybe what is the average deviation from the mean, okay? In other words, hopefully it makes sense that we might add up these values and divide by the total and see how much these values deviate on average. Again, I'm just deriving this so you get a feel for what's going on. So the first step in finding the average would be to add these values together. And so remember, we've done this operation to every single value. And so the symbol for that would be the sum of x minus x bar squared. Okay, and when you add up those values, I'm going to give you a minute to maybe kind of look at that a little bit. When we add up these deviations, what you're going to find is that these values add up to 0. Okay, and this is always going to be the case. Okay, this is always going to be the case. Okay, think about why. Remember why this is true, okay? It's always going to equal 0 because the mean is the balance point, okay? The positive and negative values are going to cancel out because the value below the mean is the same as the value above the mean. Remember we said that. And if these deviations in any case are always going to add up to 0, that means they're going to be useless to us, okay? And again, why is that happening? Since x bar is that balance point that we talked about, okay? It's the balance point, okay? So we're always going to get 0, and so that's not going to really help us when we add up these deviations. And hopefully this helps to explain a little bit more how the role of the mean. It balances the values below the mean, okay, are going to balance with the values above. So this is why you're always getting this 0. So we still are interested in the average deviation, but we're going to need to figure out how to take care of this situation. One way to do that is to take absolute values, okay, and to find out how far the values are. And there is such a measure of variation called the mean absolute deviation, but we're not going to be talking about that here. Instead, what we're going to do is we are going to square these values, because we know that when we square the values, that we're always going to get positive numbers. So what I'm going to do is I'm going to take each of these deviations and I'm going to square those deviations, okay? So I'm going to get -4 squared, which is 16. Then I'm going to take -3 squared, which is 9. Here we have a 1, 36, and 17 squared is going to be 289. 1 and 4. So now I've squared those deviations, and again, what I want to do is I'd like to find an average deviation, and in order to do that, or an average actually squared deviation, and so the first thing I need to do is to add these values together. And what I'm going to get is 356, and the symbol for that, since I've done this operation to every value, is the sum of x minus x bar squared. The sum of x minus x bar squared, okay? Now, the next thing that we would do in finding an average is we would divide by the sample size, or divide by n. And here's a place you're going to have to trust me a little bit, because it's beyond the scope of the mathematics that we're doing. But you're going to have to trust me that instead of dividing by n, it turns out that it's better to divide by n minus 1, okay? This has to do with things that we may or may not be able to discuss later in the course at this point, but it makes a better estimator. So this is going to be a better estimate of the population value. So when we take this value and we divide by n minus 1, we get something called the sample variance, okay? S, it's denoted by s squared. That square reminds you that we have gone through and we've squared things, okay? So for our A data, okay, the variance is going to be equal to the sum of x minus x bar squared, which is 356. And then we're going to divide by n. Remember, n is 7 minus 1. And what you're going to end up with is 59. I'm going to do my calculations to 4 decimal places just so that it's a little more accurate. We're going to get 59.3333. Now, the variance is used in advanced statistics for other reasons, okay? But what I do want you to know is that since we've squared everything, this is not in the units of the data. In other words, this does not stand for accidents, but instead for square accidents, which really is meaningless, okay? So it's not in the units of the data. Okay, not in the units of the data. Okay. Now, because of that, so don't put accidents, it's square accidents. But for our purposes, what we really want to do is we're trying to describe our data set. So it would be nice to be able to talk in terms of accidents. And so what we do to compensate for all this squaring that we did above, okay, so that's what this right here, what it compensates for that squaring and gets us back to that original units of measure, we're going to go ahead and take the square root. This is called the sample standard deviation, okay? So what we're going to do, and because it's in the same units of measurement, for us it's going to be a little bit more useful for what we are doing here, okay, which is describing our data set. So the standard deviation, which is just the square root, and you can see that they're squared, is going to be the square root of 59.3333, which is going to give us 7.7028 accidents. So now we are in the units of the original data, okay? So this gives us the same units, and we can talk about accidents, okay? So we're in the same units as the data. And so for that reason, it's more useful. Now, the sample variance and the sample standard deviation describe our sample. They're characteristics of the sample. So these are statistics. Okay, these are statistics. Even though I'm not going to put these on the exam, I do want to talk about the population variance and the population standard deviation. We're not going to talk about them in this context. These are going to describe the population, so these are parameters. Remember these words from earlier this semester. Okay, these are parameters. Okay, now notice it's very similar. We take each value and subtract off that population mean, okay? And so it's basically the same ideas up here. We're subtracting off the mean and squaring them. But for this variance, which is denoted by sigma squared, we are not dividing by n minus 1 because this is not an estimate. It's the actual value. So we divide by the population mean. The population size. And then the standard deviation, just like above, we're going to take the square root. What I'd like you to do is to take a minute and go back to your PowerPoint, and you'll see that they give you an example. Oops, I didn't realize this wasn't here, so now you should be able to see it. I'm going to send you back to the PowerPoint. They're going to show you the steps one more time using our big bank example. Remember the banks that we had earlier? So I would like you to go view that in the PowerPoint, and then we'll come back and talk a little bit more about what's going on. Okay? So look at that, and then we'll come back and talk a little bit more about this formula.